lesson on equilibrium involving pressure, if it's a gas, and solids and liquids. So these are the exceptions. Initially, when we did equilibrium, we talked about molar solutions in aqueous solution, molar concentrations in aqueous solution, and moles per liter. What we're going to do now is to talk about how pressure, which is a more convenient way of measuring a gas, and what happens to their solids and liquids involved in the reaction. Ideal gas law, PV equals nRT. If we divide both sides by volume, you get pressure is equal to N over V, which is moles per liter, RT. T is a constant, R is a constant, so if you have any pressures, the R's and the T's will tend to cancel out. So you can do equations in pressure, which is directly proportional to the number of moles divided by volume. So if you have H2 plus I2 is in equilibrium with 2HI, if they are all gases, you could use the pressures. And instead of having a K value, because they're proportional but not equal, you can have a Kp. The equilibrium constant in pressure is equal to the pressure of Hi squared over the pressure of H2 times the pressure of I2. And it works the same way. You plug in SI units of pressure, atmospheres. It is dependent upon the atmosphere, so you do have to do it in atmospheres. If it's not in atmospheres, you got to convert. And it works the same way. So you just plug the values in and you come up with that. I said that it's proportional. The Kp and the K is proportional, and the value of RT plays a factor. Well, the RTs will cancel out if they're the same, but if they're not the same, if you have 2NO plus Cl2 in equilibrium to form 2NOCl, in this case, you're going to have 2 moles of gas on the right, or on the top, and 3 on the bottom. So the RTs don't cancel out. If it's 2 moles and 1, 1, we're okay. But if they're not, then it's going to be off by a factor of RT to some power. So the pressure, Kp, is equal to the K value times RT, because it's proportional, to the change in moles. If you have more moles on the top, then you're going to have cancel those out. If you have less, then you're going to have to reduce it. If they're the same, you don't have to worry about it. Here, you end up with 2 moles. You start with 1 plus 1. 2 take away 2 is 0, so Kp would equal the K value in this case. This is not so. You're going to have to adjust for it. You have 2 moles here. You have 3 moles here. So the change in N is going to be -1. You're losing 1 mole. You can also think of it as right over left. You got 2 RTs on the top, and you have 1, 2, 3 RTs on the bottom. So you're going to have more RTs on the bottom, so it's -1. So in that case, the Kp is equal to K RT to the -1 for that. If you reverse that, equilibrium with 2NO plus Cl2, now you're making more gases. So this is a total of 3, and this is 2. So you are adding 1 more mole. So in that case, Kp would equal to K RT to the +1. And that's how you convert from K to Kp. On that. Now, if you have a solid, the concentration of a solid, say you have ammonium ammonium carbonate, which is a solid, will make ammonia gas and water and carbon dioxide. I think that is pause. I guess it helps if you write the formula correctly. And it should be balanced now. 8, 6, 8, yeah. Okay. So, solids cannot change their concentration appreciably. So, solids and liquids cancel out, are not used, because you cannot change their concentrations appreciably. They don't do anything for your equations. So these are all gases over here. That's a solid, so products of reactants. So here, K is equal to NH3 squared times H2O times concentration of CO2. So anytime you have a situation where you have a solid or a liquid, and the denominator, it just goes to 1. So assume it's to be 1, so you just put it down as 1. Here's an interesting one, PCl5, which is a solid, is in equilibrium. That's an equilibrium, by the way. These will only work if it's in equilibrium. If it's not in equilibrium, you can't do these equations. PCl3, which is a liquid, plus CO2, which is a gas. In this equation, the only gas is the chlorine, so the K value would equal to the concentration of Cl. And that's the only variable you would have there. Another thing that you can do is you can use an ICE table. I stands for initial, change, and equilibrium. And you'll be given an initial concentration, or concentrations, and a final concentration. So, at a set temperature, you have 2NOCl, equilibrium, 2NO plus Cl2. Initially, you have 3 molar NOCl. Amount of change we're going to save for a little bit later. And in the end, we find out that the equilibrium concentration of chlorine is 0.4 molar. Initially, you had 3 molar NOCl and no nitrogen monoxide and chlorine. So you had 0 and 0. Then what you do is you use this ICE table. 0 plus what will give you 0.4, and that's a plus 0.4. But we also got to pay attention to stoichiometry. This is a 2. So for every 0.4 moles of Cl2 you make, you will make plus 0.8 moles. So that's 0.8 there. Over here, it's a 2-to-2 ratio. So you're not making NOCl. You are removing or taking away from that. How much? 0.8. So that ends up with 2.2. Now you have your equilibrium concentrations, so you can write the K expression, which is what you have to do to start off with. If you don't, it's not correct. Squared Cl2 concentration NOCl squared. So those are your initial concentration, or that's your expression. And now you plug in the equilibrium concentration values. Just plug it in and chug it in. So that's equal to 0.8 squared times 0.4 divided by 2.2 squared, which comes out to be a value of 0.053, which definitely would favor the reactants. So this would not be a very good equilibrium expression for producing NO or Cl2. Now this ends this lesson on equilibrium, calculating equilibrium values.